Hey guys, you're watching Gamer.
Hello guys, welcome back to my channel. It's been a really long time. I finally came home after a long semester, and first of all, Happy New Year to everyone who's watching. I had my birthday, my 20th birthday yesterday, and I looked into some topics that I would like to cover on my channel. I thought, to develop that topic I need to provide some background information. So this video is essentially about that. Let's get started. So first of all, let me just define a matrix, and this video is about matrices for the most part, with elements say A11. This is say A1, and this is a square matrix, N1, Nn. And when I denote an element like this, I is the row and j is the column. So I'm gonna keep this notation consistent throughout this video, and this is the predominant notation. Okay, so now let's define this quantity. The minor of element a sub ij, and we're going to denote that with m sub ij, is actually, well, this is a quantity. And how do you compute this quantity? Cover row I and column j, and take the determinant of the remaining terms. So for example, for element or row 1 column 1, that will be minor 1 1, based on what we defined on top, is just the determinant of, well, you exclude the first row and first columns. So you have A22, AN2, A2N, ANN. The top row and first column, they're gone because we have to cover or sort of not consider them in this determinant. This is the minor of an element of a matrix. Another quantity we will define is the cofactor of an element. It's connected to a minor because cofactor, we can write that as c sub ij, is minus 1 the I plus j times the minor at that position. So there is this sort of this negative propagation going on. So in the case of a 3 by 3 matrix, let's say we have the identity matrix. The positions with which will sort of have a negative sign, where this I plus j term will be r, is this for 1 plus 2, this 2 plus 1, this, and this. So they form this sort of diamond, this quadrilateral, and that's just for n equals 3, three-dimensional square matrix. Okay, now one important thing I want to talk about, or at least address briefly, is the cofactor expansion. Why are cofactors important? It's because of this cofactor expansion of the determinant. So we can find the determinant using the cofactor. Wait, doesn't this sound circular? Because we used the determinant to define what a minor was, and now we're gonna use a cofactor which has a minor baked into it to calculate the determinant. Well, the thing is, it's the way I like to think about it is, it's a determinant is sort of a quantity that's guaranteed to exist in linear systems, or you can define a determinant always. And since it's unique, if you construct one such construction which satisfies all the properties of what a determinant should, which includes multilinearity, anti-symmetry, and a bunch of other things, and because of uniqueness, then that has to be the determinant. So what you can do is you can define a determinant for a 2x2 system, and you can have everything be sort of like a recursive case of that. You can define the determinant for 2x2 system to be AD minus BC, this product minus that product, and then all the other determinants, because all the other determinants sort of will recursively build on top of this, because this itself, once you say determinant, you have to basically go inside this and do another cofactor expansion, as we will talk briefly after sort of this idea. But so there shouldn't be really much problem with the circularity of this thing, because I'm gonna use the 2x2 determinant as sort of a base case, and then everything else will sort of recursively build on top of this base case based on the formula that I'm about to give. So the formula, determinant of A is the sum from I equals 1 to n C sub ij A sub ij. So in this case, we're summing over I. We're summing over I, and we're fixing j to basically take any value between 1 and n. So if you fix j and sum over I, and where j is your column number, this is called the column expansion. Whatever you fix, you're expanding about that. So this is the column expansion. And if you fix the row, it will be a row expansion. And Cij, of course, is the cofactor. A sub ij is the element of matrix A. So if we do an example, determinant of 212, 311, 528 equals, well, I'm going to expand about the first row. So I'm fixing my first row while I sum over the column now. 3 columns. So 2, that's the first element. That's the A11 term. And now the cofactor term. So cover this row, this column, you have 1128 inside for the minor bit. And then you take the determinant of that. Now we have a minus because of this formula and this observation. It's on the minus spot. So 3. Cover this row, this column. So we have 1, 2, and 2, 8. Plus 5. Cover that row, that column. We have 1, 2, 1, 1. And if you calculate these out, and I gave the formula for the 2x2 case, calculate those guys out, you get some answer, which I'm not going to calculate and waste time. which will indeed be your determinant. So this is a formula, a cofactor expansion formula for the determinant. I also made a video on the Dodson condensation method for calculating the determinant. Please check that out. I also included many other things in that video, so that video is pretty important. This is Laplace's cofactor expansion formula for the determinant, the most popular formula. This is what they will teach you if you do linear algebra or the basic number crunching linear algebra in high school or at university. Now let's come back to what's of importance here. So if you remember linear algebra, you might remember, if you don't want to get interested in anything else, linear algebra is a way of solving simultaneously several equations. So assuming you have like equation 1, some a1 x1, a11 x1, a12 x2, a1n xn, a21 x1, a22 x2, where all these a's are basically coefficients, equals, say, I don't know, b1, b2. Keep sort of doing this. You have n different equations and n unknowns, so it's a consistent system. If you have too many equations, then a solution may not exist. If you have few equations and many variables, you might introduce some linear dependence, or so this is a consistent system. If at least you want a unique solution, you want n equations, n unknowns, hence we deal with square matrices, so it's all connected. Just finishing this off. The best thing about linear algebra is you can represent all of this junk with something like this: a acting on x equals b. So where a is like a matrix with like all of those coefficients in it, and then x is the column vector of unknowns, so x1 to xn. B is basically what all is there on the right hand side of the equations. And the way matrix multiplication works, if you do the multiplication for b1, you'll get exactly the first equation. So this is a way of rule keeping or equation keeping, writing them as one system. And now how do you solve such a thing? Well, x is a inverse of b. So we define an inverse, and let me say the inverse matrix looks like this: d11. These are the elements of the inverse matrix. There's a formula for that to calculate the inverse. See the ijth element. You invert the original matrix A. Sorry, you transpose it. So make the row the column, and then take the cofactor at that position. So the transpose and the cofactor I'm going to denote as a flip of the subscripts, and normalize it by the determinant of the entire original matrix. So that's why, if you remember your linear algebra, they said an inverse does not exist if the determinant of the matrix is 0. Now you see why the denominator blows up here. And why does this work? Well, this is say A inverse, right? This is say this is A inverse sub ij, for example, just to be a little more consistent. Why does this work? let's say A inverse A, if you want to write that out, is sum j equals 1 to n d sub ij a sub jk, and then sum j equals 1 to n a sub jk c sub ji. We can switch them around, they're just elements or numbers, so we can, the order doesn't matter here, it mattered for this matrix multiplication. And now if we just sort of take the determinant of A outside and sort of expand it for a few terms, 1k, 1i, 2k, 2i, nk, ni. So you notice what's going on here. This looks a little like the determinant formula we had on the previous page. Remember, determinant of A, sum from I equals 1 to n, Cij, Aij. This looks a little bit like that if you just expand it out, you know, for some terms. This looks a little like that, except the problem was the j's were the same. Here the k and the I, they're not the same. So I mean, they could be the same, but let's first consider case 1 where I is not equal to k. This could almost be the determinant, except this is not the determinant of the original matrix. This is the determinant of sort of a modified matrix where the ith column is actually the kth column from the original A matrix. So this is the ith column. So the ith column is replaced by the kth column from the original matrix. But now the issue is when we take the determinant of this thing, that's what this expansion is, right? The determinant of this modified matrix. The kth column, when we do the cofactor expansion, we ignore all of the ith column, but the kth column is still there, right? Because we ignored the ith column, and in the modified matrix we pull a separate kth column to put it in the place of the ith column. But remember that the kth column is different from the ith because I is not equal to k, so that kth column is still there somewhere. It's not at the ith position like you know, in the modified, like for the modified matrix we just pull that in here. The kth column is still there at the kth position, and both these k and I positions are not the same because we just sort of use that. And since the determinant of this is basically this expansion in the bracket here, notice this will go to 0 because the determinant of a matrix which has two columns which are identical is 0. This is one of the properties. You can use anti-symmetry to sort of prove this from the main properties of the determinant. Okay, and this holds true for arbitrary I and k which are not the same. The second case is when I equals k. That's when you're basically writing out the column that we ignored during the cofactor, when we found the cofactor out. So this is, you have an I here. You have an I here instead of a k because I and k are the same. And since this was the column we excluded in the cofactor expansion, it's not present anywhere else. And then again, even if you want to use this formula and see when I equals k, you have AJI, CJI. That's basically the expansion for this determinant. it's the row expansion for this determinant. Here we expanded by a column, but also expand by a row. So when both of them are the same, this is just the determinant of A. So combining all of those cases in, when I equals K, you have a determinant of A divided by determinant of A, which is 1, and 0 regardless. So we have a Kronecker delta, but it's basically a matrix, right? Because it has these indices running. So when I equals K, that's like the diagonal position, the principal diagonal position. We have 1s there and 0s everywhere else, which is precisely the identity matrix. So A inverse times A is the identity. You can do a similar approach for A inverse, in which case you'll have to look at not the rows but like the columns and conclude the same result, because the determinant of a transpose is the determinant is unchanged over transposition. And you'd have to use this first form for the determinant, but you would get the same answer as using this row expansion. So I think that this kind of makes sense, and like, again, uniqueness of the inverse for invertible matrix with a non-zero determinant, and you get this nice result, this formula for the inverse. Well, why is any of this useful? I mean, you could in this to find x, what you could do is just invert A and then multiply that by B, but this is just the classic method. You call it Martin's rule or whatever, but I'm gonna introduce Cramer's rule, which is sort of, I feel, a little more general method of finding the solution for such systems. It directly gives you the solution. You don't need to find the inverse separately and then multiply it, because sometimes matrix multiplication is really awful. So for this, we have X is basically A inverse acting on B. So Xi is sum from j equals 1 to n dij bj, where dij are the elements of the inverse. Let's sort of expand it for when I equals 1. So we have d11 b1 plus d12 b2 plus d1n bn. And if you want to write this in terms of cofactors, that's also fine. C11 B1, C21 because of the transpose during the formula for the inverse, if you notice. Cn1 Bn. There should be a 2 there. This is column expansion. But what is this? If you remember, how we justified the inverse, or what the argument was, that this is basically the determinant of a modified matrix with these A's, these the kth column of the original matrix A in place of the ith column, which was omitted because of this cofactor. So this is basically the determinant of a modified matrix. This inside bracketed term is the determinant of a modified matrix. So let's call it A sub I, because we're replacing the ith column. Or we're doing it for 1, so A sub 1. The determinant of B1 Bn. So we replace the entire first column of original matrix A with these entries B's, because it's already in a column vector. So you just take all of those and replace the first column by them. Everything else remains the same. and that's for I equals 1. We can generalize this for an I so this is at the ith column position. And we take the determinant of this modified matrix, and that's just the bracketed term, and we still have to divide by this determinant of A. So xi in general just becomes this stuff here. So determinant of A bracket I, so that's the modified matrix that we talked of, where we replace the ith column with the elements of B, over determinant of A. That's the formula. That's what the formula for Cramer's rule says, and this directly gives you the unknown x. Don't need to multiply anything. And again, if determinant of A is 0, the solution is there is no solution, or the matrix is not invertible. If both of them are 0 for all I, then there could be a chance that there is a solution, but we have to introduce some linear dependencies then. Otherwise, if the denominator is 0 for any one of them, it's inconsistent, so forget about it. This is Cramer's rule. I mean, classically it's not really that important, except for it feels more natural when we do it this way, because that's how we actually define this inverse here, by just using this observation of a determinant of a modified matrix where we replace the columns. But this will be extremely useful for what we're going to do in the next video, hopefully, and we will try to generalize, spoiler alert, the Wronskian. So we have an n-dimensional Wronskian for linear nth order ODE. So I hope you stay tuned for that video, and I promise I shall be more regular. Please like, share and subscribe to my channel, recommend me to your friends, spread the word. In the meantime, stay home, stay safe. Omicron variant out there. Keep doing math. Peace out.